problem is a ladder of 5 meters long rests with one end against a vertical wall of height 3 meters and the other end on the lower ground. If its top slides down at 10 centimeters per second, find the rate at which the foot of the ladder is sliding. So I've just drawn a little picture here. So this height is 3 meters, this is 5 meters, and this is a ladder of constant length, and they say that this end right here is moving at what, 10 centimeters per second. I don't have space there. I write it here, 10 centimeters per second. Okay, and they're asking us this velocity here, this one. So what is that? What is that velocity going to be? So the and they are asking us the velocity at this moment only, because it's going to change later on. So we can use calculus, but for this problem I'm going to use both. Okay, so I'll just make so this is calculus, and that is my first part, and this is by, you can say, the normal method. So using calculus, I'll do that later on, but the simplest method is to realize that the length of this ladder is constant, right? So the velocity of this point in this direction must be the same as this point's velocity in this direction. So you can kind of view this as a vector problem. You know, this has a magnitude of 10, so you can break it into components, having these two components, and this vector, yellow vector right here, into this and that, right? And we are interested in these components right here, these and this. Okay, so what is the component in this direction? This one. Well, it's going to be, if this angle is some, let's say, theta, then this velocity, which I'll call v1 will be equal to 10 cosine of theta, right? Oh, I'm doing this in the calculus part, so sorry. So v1 is 10 cos theta. Okay, and for simplicity, I'm just going to do a little simplification here. I'm going to make this centimeter, right? Alright. Okay, so v1 is 10 cos theta, and what is this velocity? It will be this, which I have to find out. Let's say it is u. It will be u times the cosine of this angle, this angle right here, and that, I believe, is the same as this angle, which is 90 minus theta, right? 90 minus theta. Okay, so now using Pythagorean theorem, we can say that this side is 4, right? Pythagoras theorem. So what is the I guess you could say tangent of theta? It is 4/3, 4 by 3, you can say. So theta is tan inverse of 4 by 3, which I believe comes out to be 53 degrees approximately. Alright, so what to do next? Well, now this angle is 53, so this angle is going to be 37, right? So 10 cos theta will be 10 times the cos of 53, which is you can see it is 3 by 5, right? So 3 by 5 times 10 is 6, I believe. And if I call this v2, then v2 is u cos of this angle, this angle right here. which I told you that it is 90 minus theta, which is we just figured out it's 37 degrees, right? So this is cosine of 37 degrees, which I believe is 4 by 5, right? Yeah, so this is 4u by 5, right? And I guess that v1 should be equal to v2. That is a must, because if that wasn't the case, then the length of the ladder will change. So that's clearly not the case, so they have to be equal. So which means that these two have to be equal. So I guess we could solve for u then. So we have that 6 is 4u by 5, so u is 30 divided by 4, which is 15 divided by 2, which is 7.5 centimeters per second. Okay, so that is the velocity using the normal method. And you will see that things get a little bit complicated in the calculus method, but it's quite useful to know, because you might have to use that, right? Okay, so if I'll make a fresh diagram here. If this is my ladder, including this is 5, this is 4, this is 3. Okay, and I'll call this h, okay, and I'll call this x, just for a variable purpose, because it's going to change, right? Okay, that's h, that's x, and that's not 4 times x. Okay, so just be careful there. Okay, so what have they given us? They've given us this velocity, right? This. And what is that velocity? Well, that is 10. And we know that must be equal to dh dt, because that is the definition of velocity, right? And we want to figure out dx dt. What is that? Right? So we can use the condition that h squared plus x squared is going to be 25, which is 5 squared, right? And this will be always true, because this will always be a right triangle, so they have to agree with the Pythagoras theorem, right? So okay, so that should be the necessary condition. So what if I differentiate both sides with respect to time? And I believe you know this is somewhat an implicit differentiation, so I believe it will be this, right? And on the right hand side you'll get 0, because the derivative of the slope of a constant line is 0, right? Okay, so what is h at this moment? Just pay attention to that. At this moment, right? H is varying, but this h is the momentary h, right? So what is that? That is 3, right? So that is 3 times 2, which is 6 times dh by dt. We just whatever. Okay, and what is x at this moment? It is 4. 4 times 2 is 8 times dx dt is equal to 0. So if we solve for dx dt here, we will get 6 times 10 is 60. What will I get? I'll get minus 60 by 8, which is minus 30 by 4, which is minus 15 by 2, which is minus 7.5 centimeters per second. And you'll notice that I got a negative sign, right? And that's because if I assume this downward as positive, then automatically yeah, that's correct. So automatically the left word direction, this becomes positive, right? So whatever is on the right will become negative. So u is to the right, right? Like this. So that will come out to be negative. So that kind of makes sense. So yeah, the final answer is 7.5, but I guess in this problem you could more preferably use the normal method because it's kind of short, right? How much is that? 4 lines, and this one took quite a bit of time. But calculus is a thing of its own. It has its own uses. It's a beautiful method. You might be asked to do the problems using calculus method, so you can just if your teacher says that you have to do by this method and all that, you can just say that, see ma'am, this or sir, whatever, this is also a valid method, right? It's kind of based on logic. Okay, so yeah, that's it, and I'll see you in the next video.